Good afternoon, everybody. How are you doing? Oh, wonderful. Okay, I got at least one wave from the back. Hello, everybody. How you doing? Oh, there we go. I know it's a little bit warm, so don't want you all, normally I tell people to do jumping jacks before these talks, but given that it's 80-some degrees outside, I think we'll pass on that opportunity. So I'm Brian Kloppenborg. I will be both the first speaker, so I get the privilege of introducing myself, and also the MC for today's session. Peter Bilo, who normally hosts these sessions, couldn't be here with us today, although he might be here tomorrow. So if you are looking for him or you're looking for the AVSO, we're just the tent that's right up the hill, just off to the side of the pavilion here. I guess I can introduce myself and say that I'm going to be the best speaker today because I'm the first speaker, right? And I also get to abuse this privilege here. But actually, I'm an astrophysicist by trade, and I'm also the executive director of the AVSO, and I hold a PhD in physics from the University of Denver, and a BA in physics from Hastings College, which is a small liberal arts college in central Nebraska. Previously, I worked as a research scientist at Georgia Tech Research Institute, leading a variety of teams on different government programs. And I've published in, my first publication was actually in the Journal of Nature, but I've also published in the Astrophysical Journal, and I mostly now focus on fostering pro-am collaboration. So without further ado, hello, Brian Kloppenborg. All right, so let's get my timers set up here. Thank you. All right, so today I'm going to be talking to you about spectroscopy, which for those of you that know the American Association of Variable Star Observers, actually, could I get a quick raise of hands? Who's heard of the AVSO before? All right, everybody good? Who knows what we do? Okay, all right, so somebody shout out what we do.
Collect data on variable stars.
Collect data on variable stars. What kind of data? Photometric data, so that is one thing that we do. So that's what we're actually best known for, but we actually have 4 separate different types of programs that we collect data on variable stars for. So photometry, of course, is the thing that we're best known for. That's the measurement of brightness over time, so as stars get brighter and fainter, we record that. We've also collected sunspots, so if you don't like being out at night and you'd rather be out during the daytime, we've been doing sunspot counting since 1945, and right now our data is actually being used to cross-reference and cross-calibrate a group that's been around for much older that exists over in Belgium, and so this data has proven to be exceptionally useful. We also have operated a spectroscopy program since, I think, 2015, 2016, and I'll be talking a little bit about spectroscopy today. And if you guys want to participate in kind of state-of-the-art programs, we also have an exoplanet observing program, and we slide that in under, our charter was variable stars and kindred subjects. So, the exoplanets, it's a 1% variable star, so we're going to count that in under that program. So if any of those things sound interesting to you, feel free to come up and talk with me after my talk, or just visit up at the booth that will be here for the rest of the week. All right, so I'm going to present this talk in a little bit different than how I normally do, and it's going to be more of an introductory talk, a more overview of the field of spectroscopy, because like all the fields that we participate in, once you start digging into the details a little bit, it really becomes a very diverse and fairly complex field. So I'm just going to skim the top of it today to give you a bit of a primer on the different things that you might be able to do if you were to have a spectroscope. So we're going to start off by talking about what is a spectrum. We'll talk about the different types of spectrometers that you could potentially purchase, and I'll have pictures of a bunch of different commercial units that you could buy. Talk about the data collection, reduction, and calibration steps that you would encounter and the types of projects that you can do with relatively modest setup on, say, your backyard telescope, because you actually can contribute useful data with a 8-inch telescope, for example, with a spectrometer on it. And then where you can learn a little bit more and submit data, not only to the AVSO, but a couple of different organizations as well. All right, so the basis of spectroscopy. So how many of you have seen this gas discharge tube in like your high school physics class? Right? You remember that? Everybody loves those things. They're really cool. So if you take the light from one of these gas discharge tubes, and the center section is what would illuminate on the left, and you throw it through a prism. We heard in Mitchell's talk last night, he had a really, I'm going to steal that diagram that you had. That was wonderful to explain it. But if you take that light that comes from the gas discharge tube and you send it through a prism, it'll disperse into a variety of different colors of light depending on the element that's inside of the tube itself. So in this case, we have a tank of hydrogen here, and then the lines that appear on the right-hand side. Who knows the one to the far right? What line is that? That's something that you might have a narrowband filter for. Hydrogen alpha, right. How about the kind of teal-colored line? Hydrogen beta? Yep, so this is the full hydrogen series that you can see. And if you take the brightness that you see in the upper image and you convert it to the lower image, where you plot the intensity along the vertical axis and the wavelength on the horizontal axis, that is a spectrum. And you can see that there's basically no light for the majority of the spectrum going across horizontally, and then where those spectra appear, where the bright lines are at, you get these big spikes, and that corresponds to the emission lines of hydrogen. Now, there's a variety of different parts of a spectral line that I might discuss here. So that flat part that we saw a little bit ago, that's called the continuum. It can either be completely flat or it might be sloped depending on the type of object that you're looking at or how you've reduced your data, but in either case, it's called the continuum. Where the continuum starts to slope down into kind of the trough area, that's called the wings. Those are areas that are Doppler shifted either red towards the red or towards the blue. And then finally, the furthest down at the bottom, we call that the core of the line. Now, how do these lines form? So who would like to have a lecture on quantum mechanics today? Okay, sorry guys, I'm not going to do that. But here's kind of the basics. So if you remember like the Rutherford model of the atom, we were thinking about electrons being in orbitals around the nucleus. And when you send energy into the atom, you take the electron and you bump it up into a higher orbital state. And then after some period of time, due to quantum mechanics, the atom will relax, and then the electron goes down from a higher energy state to a lower energy state. And whenever an electron goes up or down in those energy states, it has to either absorb or emit energy respectively. And so here's a couple examples of different hydrogen series that you can have. The Lyman series, this occurs way off into the ultraviolet, so these are things that you wouldn't see. The Balmer series are the things that most of us are familiar with, so that's where the H-alpha line comes from. That's the 656 nanometer line, and it goes from this n is equal to 3 to n equals 2 orbital state, so going from a higher to a lower orbital. But then all the rest of the lines that you see down here in terms of the kind of teal out to the violet ones, those are all represented there as well. I've done a lot of work out in the near infrared, and so I actually work with the Paschen series a lot more than anything else. But this is how the lines actually appear and disappear. So whether it's in absorption or in emission, this is where it should occur in the case of hydrogen. Now, other atoms, so like if you were to go to helium or heavier atoms, or if you go to molecules, they all have absorption spectra and emission spectra, so they all have their own kind of unique fingerprint that goes along with them, and it depends on the composition of the material that you're actually looking at. The next topic I'd like to discuss just briefly is blackbody radiation. So who has like turned on their stove and watched as the old coiled electric burners, they get hotter and hotter, they start to glow? You've seen that before? And so that's a form of blackbody radiation where as some things get hotter and hotter, or like, did I hear that there was a blacksmith here at one point, or maybe not? But as you get metal hotter inside of a furnace, it starts to glow. It'll grow kind of like a light color to begin with, and then it'll start getting hotter and hotter. It'll go through the reds and then the oranges and then up to white. So as the material is getting hotter, it's becoming more and more emissive. It's releasing a lot more energy in the form of light, and that's blackbody radiation is what you're seeing there. And so these curves here show basically the amount of light on the vertical axis coming out as a function of wavelength along the horizontal axis at different temperatures. And so our stars, like if you probably got to see Antares up there in the sky last night, a beautiful red star, right? So that's a relatively cool star, and so it'll have a temperature, I don't remember what it is offhand, but it would have a temperature kind of like maybe in the 4,000 to 5,000 kind of Kelvin range. Whereas if you were to look at a hotter star like Vega, it might be something that's hotter like 6,500, maybe 10,000 Kelvin or something like that. And so just the emission of light from these objects it causes them to emit light, right? But you might also notice that these curves, they change their shape, and the peak location curves and changes from off to the right at 3,500 K, it's relatively low. You don't have a laser pointer, do you? Nope, okay, sorry. Sorry, guys. So at 3,500 Kelvin, the peak of that line is relatively low, but as you move up to, say, this 5,500 Kelvin, right, the peak comes up here. And so you can see as things get hotter and as they go from cooler to hotter, the peak shifts from the right to the left. And so you get different amounts of light of different wavelengths. So now if we put the concepts of these spectral emission or spectral absorption lines together with blackbody radiation, we actually can get the spectra of stars. And here on the left and the right, I'm showing the same information, but on the left-hand side, this is an absolute scale. So you can see these hotter stars, like our O stars, they have their peak that's way off to the left. However, if you go down to like the K0 star, so that's the third from the bottom, the peak is more like in the 5,000 Kelvin range. And so you can see as a function of temperature, that slope of the line changes and it comes and it curves down. That's the blackbody radiation effect that we saw a little bit ago. And then we see different atoms appear in the atmosphere depending on different temperature and pressure conditions. So on the right-hand side, what we've done is we've subtracted out the blackbody radiation effects, so now the whole spectrum has been normalized so that the continuum has a value of 1 and it's flat. And we can see all of the absorption lines, or I guess there's no emission lines in any of these spectra. You can see them that are all listed here. So if we look up at the top at an O star, these are very hot stars and they're capable of ionizing not only hydrogen, but also ionizing helium. And so you get absorption lines of helium that appear in the spectrum. So you can see this helium-2 line. And as we go from warmer stars like an O star here at the top, down to cooler stars like a G2, notice that that helium line disappears. That's because the stars aren't hot enough in order to ionize helium anymore. Whereas if we look at some other lines, say like, let's pick another one. There's a helium line there. Another one that has a good effect here. Actually, we can look at this. This is the H beta line, but it's also a blend with helium-2. You can see that as you get cool, like go through the middle temperature stars, so an A star, again, that's going to be kind of 6,000, 7,000 degrees Kelvin. The line there becomes the deepest that it possibly can, and then as you go to cooler and cooler stars, you can see that the line starts to get filled in. And so you, by looking at these different absorption and emission lines, you can actually infer what the temperature and pressure conditions are inside of the star. So that's how we as astrophysicists are able to infer, what the stars are made out of. And that's a really cool thing. Just as a quick quiz, does anybody know who discovered that the sun was made out of hydrogen and helium? I'll give you her first name, Cecilia. Cecilia Payne-Gaposchkin, exactly. So absolutely wonderful person, and she went to a lot of hard work to try to figure that out, and it's not, I would say, appropriately recognized for the work and the work that she contributed to astronomy. Now, in addition to showing temperature and pressure conditions, spectra can also show the motion of stars. So you know how if you hear a train or an ambulance go by, you hear the pitch of a siren is relatively high-pitched, and then as it goes past you, it goes to a lower pitch? That's the Doppler effect. The exact same thing that happens at audible frequencies, things that we can hear, also happens to light as things move back and forth. Although it's not really a significant effect, but it is something that we can actually measure from here on the ground. So if we imagine that we're this happy face down here in the corner, and we have two stars that are orbiting around each other, the star in they're rotating in a clockwise direction. The star in the upper left-hand corner, it's moving away from us, and so its light is going to be red-shifted. The star on the right-hand side, it's moving towards us, and so its light is going to be blue-shifted. Now, if we take and we were to plot, say, the motion of these two stars, looking at, say, a single spectral line, we could come up with the spectra are there in the middle. You can see with those two blue lines that I put in place there, you can see that the lines are not always in the constant position. And then if you go look on the right-hand side, you can see how they're kind of making a sinusoidal pattern back and forth. That's actually looking at the orbital motion of the stars. And by just a little bit of math, you can take a diagram at the right-hand side and you can figure out how fast the stars are moving around each other, usually in the kilometer per second regime for amateur-grade equipment. If you're looking at exoplanet stuff, that's not doable by amateur equipment. It requires extremely stabilized equipment, but they can get down to like meter per second level. So this is like walking speed. You can tell a star is moving at you or moving away from you at meters per second speed, which is just really phenomenal to think about, that we can measure things that are that fine. All right, next up, let's talk about data collection. So there's a variety of different types of consumer-grade spectrometers that if these sort of things are interested to you, you could consider purchasing. The first of which is a prism-based spectrometer, and the way that it works is the light will usually enter from, say, on the left-hand side through a slit. It'll go through a prism and be dispersed into the various colors, and then you collect the light on your camera. There's also transmission grading spectrographs. So these are relatively small devices. If you have a filter wheel for your camera, you can buy one of these Star Analyzer 100 or 200 devices, and it just sits in your optical path just like a normal photometric filter or like an H-alpha filter would. And in this case, the light can go through a slit, although sometimes, actually most of these devices, they don't have slits in them at all. And the light goes through this diffraction grating, and it disperses the light off to one side. And so the neat thing with this is you end up on the right-hand side, you can see there's a picture of the star, but there's also a picture of the spectrum that's right above it. So you get the 0th order, which is the star, plus some additional wavelength information off to the side. And then some of the more expensive devices, they use a reflective grating type device where instead of allowing the light to pass through it, you end up having the light reflect off of it. Normally, you ignore the 0th order, which is the white light that comes through the slit. It bounces off the reflective grating and ends up, in the most vertical direction. But you do catch the spectrum that sits down below it. And if you want to get really fancy, you can also look at these shell-type spectrometers, which have a combination of a standard grating and a specialist shell grating, which takes and it aligns the different orders of the spectrum so they stack up on top of each other, and you can get something that looks like this here. And so this is actually the spectrum of the sun provided by the Australian National University. And so you can see all types of different absorption lines there in the spectrum, and if you wanted to, you could actually go get a fingerprint of each and every single one of these elements and figure out what's in there. Do any of you recognize any prominent lines in there?
Sodium.
Yep, the sodium, the kind of in the sodium doublet in the yellow. I'm sorry, I don't have a laser pointer, otherwise I guess I could point it out. So sodium doublet's kind of here and here. Now, one thing that you have to consider when you're looking at these different spectral devices is how much resolution do you want? And this is a good illustration of if you go out and you're looking to purchase one of these things and they'll say the resolution is R, and then they give a number. This is a great way to visualize what it would look like. Basically, the higher the resolution, the finer details you're going to be able to see in the spectrum. In the case of most consumer-grade spectrometers, that also correlates to a smaller amount of wavelength that you're going to be able to see. So the lowest resolution spectrometers, these star analyzer devices, they can actually see the entire spectrum of a star, all the way from basically the ultraviolet sensitivity of your camera, all the way out to the near-infrared sensitivity of your camera. However, the high-resolution devices, they'll often narrow in, so you're only looking at, say, maybe 10 to 20 angstroms worth of, 1,000 angstroms worth of the spectrum, and they'll have much higher resolution power. But as you go from the top one, which is the top trace there, which is a high-resolution spectrum, down to the lower one, you can see that the spectrum has kind of been convolved or fuzzed out a little bit. Now, a lot of people think that you have to have really high-resolution data to be useful. However, for transient events, like who doesn't like an explosion, like nova, supernova, it's actually very useful to get these low-resolution spectra because you can see if they have hydrogen, if they have helium, if they have neon. You can see these things without necessarily having a high-resolution spectrometer. And you can also follow these stars for a much longer period of time. So when a person with a high-resolution spectrometer can't see the object anymore because it's too faint for their equipment, you can keep going like another magnitude, maybe 4 magnitudes fainter than what somebody with a much larger telescope and a much higher resolution spectrometer can. So they're pretty interesting devices there. So here's a couple examples of different consumer-grade spectrometers, as well as like how you make them, whether they have slits or not, and some examples of what they look like. So a little bit ago, I was mentioning the Star Analyzer 100, 200 devices. These are literally just filters, basically, that you put into your filter wheel. You tell your control software to move the filter in place, and boom, you got a spectrum. That easy. They do have a little bit of spacing requirements. Like ideally, they're a little bit further away from the sensor than what a normal filter would be. However, if they're a little bit closer, that's okay too, right? For example, I have one of those in my system, and I don't bother trying to optimize the distance because it's good enough for the science that I'm trying to do. So if you like to DIY stuff and you like to 3D print things, you can look at things like the low spec or this Flex Spec 1, which is a fairly recent device. They have, kind of low to high resolutions. So a low resolution device is kind of like 100, 200 in terms of the resolving power. Medium resolution device is about 1,000 to maybe 2,000, and then the high resolution devices are kind of like 10,000 and plus. And for the ultra high resolution stuff, these are the things that folks look at exoplanets with. It's going to be like a 100,000 or more, but that's not obtainable using consumer grade gear. Just a couple of different devices that you might consider. A prominent company in this area is Cheliac. They're a French company, and the guys there, they're really interested in promoting spectroscopy generally for the greater public. So they have basically something for almost everybody. So what about data collection? So I heard people cussing out their equipment last night on the observing field, and so we all love our equipment. Everything always works, right? So I guess. When you go out and you collect spectra, it's fairly similar to doing astroimaging. There's a standard set of things that you need to collect, and there's things that make your life a little bit easier if you collect certain types of data products. And so I would say that at the start of every single night, you need to collect calibration frames. These are going to be your bias, dark, and flats. So that sounds familiar for those of you that do astrophotography. It's basically the very similar process to what you would do in astrophotography. Then for each science object, you need to focus on the spectrum as opposed to focusing on a star. You have to focus on the spectrum instead. You have to set your slit orientation, take these wavelength calibration images, which are called arcs. And what these are is you have a gas tube of something in the way that allows you to get very specific spectral lines. There's a variety of different devices that you can have for that. Sometimes you can even calibrate off the sky, depending on where you're looking off of just lines that are in our normal atmosphere here. After that, I recommend that you take a reference star image, usually an A05 star. Those are the kind of featureless spectra that are really useful for flux calibration. To go observe your science object, catch your second reference star, and then do wavelength calibration again. Any idea why we want to do wavelength calibration at the beginning and at the end? Things move around, yeah, right? So the temperature of the whole system has changed, and so as the optics expand and contract, it'll actually move your wavelength calibration back and forth. These are very, very sensitive instruments. And then at the end of the night, take some calibration frames. Just in case, I guess I went over the things on the right-hand side for focusing and flats and arcs there. As for data reduction and calibration, the great thing is there's a lot of software out there that can help you do these things, so you don't have to go and invent your own wheel. For your reduction processes, every single software package that does spectra for amateur-grade equipment, it'll include things like bias subtraction, dark subtraction, flat fielding, and the latter kind of tools, and you don't have to worry about writing software to do that. And then for calibration, they also have a variety of different calibration things that you can apply. There's some kind of rules of thumb of the different techniques that you should use, and I would recommend if you're interested in these things, come up and talk with me afterward about given what spectrometer, what order of wavelength calibration could you use. Quite often, when I see spectra come into our database, people have overfitted their data a little bit too much, and so they can end up having one of their spectral lines get shifted to the right or the right to the left a little bit because they allowed too many free parameters in their spectrum. So normally you try to use a model for your data that's as simple as possible. And a couple of different things, sorry I forgot here. So in the upper right hand corner, this is a picture of RSpec. This is software that works with the Star Analyzer 100 200s, and the workflow there is basically you take your image that you have. RSpec allows you to rotate the image and then pull out the spectrum that's actually located there, because quite often your the diffraction direction and depending on where your telescope is pointed, right, the spectrum will actually rotate within the image. So they have all that stuff that's built into them. And then if you have a Cheliac product, you can use Dimitra, and I would highly recommend if you do have a Cheliac product that you use that, because it has a lot of really nice automated workflow items that make it easy to use. So here's all the other software that I know about and kind of like the prices of things. So Visual Spec is freeware. There's RSpec, which is the only commercial software that's on here. It's $109. but the gentleman that writes it provides really excellent support. And I've asked him questions, and he'll reply within 10 to 15 minutes sometimes. And so, incredibly good customer support. So $100, I think, is well worth it. You also have the unfortunately named ISIS software, as well as the British Astronomical Association. They have their BAS software, and then SpecInti, and then Demetra, which I mentioned a little bit ago. Now, which software package you use depends on what instrument that you're using, but I've kind of cross-referenced them with both slitted and slitless type devices. Now, spectrometers are tricky, though, right? So if you're used to just doing astrophotography, you know that there's a lot of different gotchas. Well, spectroscopy increases the number of them almost exponentially. And so one thing to note is that when you go out and you purchase your spectrometer, note that it's usually going to be designed for a specific F ratio. So if you have a spectrograph that's designed for, say, like an F6 system and you have an F10, you're probably okay. But if it's designed for an F10 and you have an F6, it'll actually cost you resolution because the light will be converging too quickly at different portions of the optical system. Quite often, consumer-grade spectrometers, they have different modules that you can plug in to adapt to different F systems, but different F configurations, but not all devices actually have that capability. I would re-emphasize here that having good reference spectra are incredibly important. A lot of the software nowadays and a lot of the instructions for how to use the software allow you to skip this technique because you have to go out and collect a spectrum. This is going to be like 10 to 15 minutes a time, and then you have to go look at your science object. That's 10 to 15 minutes a time, and then you go back to your reference spectrum. So you spend like 30 minutes collecting calibration data and 15 minutes only collecting the science data. However, in a lot of cases, collecting the calibration data is really important because it allows you to find small flexures in your system and get much better calibration out of it than what you would otherwise. So please do that. Next up is that a lot of people, they forget that the atmosphere itself is a prism, and they don't remember if you have a spectrograph with a slit in it, you actually have to rotate the slit, which often means like rotating your spectrograph on your telescope as well. Because what happens is as light goes through the atmosphere, it disperses it a little bit. And if you have the prism in the wrong direction, you actually cut a little bit of the dispersion out, or you add extra dispersion in, and that can cause a variety of different degradations in the quality of your data. All right, so a couple of different applications that I'd like to point out to you. So these are all papers that were recently published that are using data from amateur spectroscopists. The first of which is the orbit of this, it's a single line spectroscopic binary, so we only see one of the stars rather than both of the stars, and there's a variety of reasons why that can happen. But here you can see for V1362 SIG, you can see in the upper right-hand corner that this data from an amateur astronomer was taken in silicon and helium and H-alpha and iron lines, and they used all of this. You can see that wavy, that sinusoidal pattern that we talked about a little bit ago. They took that, and the professional astronomers in this paper here, they not only did they use the data on this BE star, but they also cited the author, the amateur who was collecting the data. And so I think it's really wonderful when you can see that type of collaboration. Next up, there's an S-type Mira variable. So Miras are radially pulsating stars. So people think stars are usually relatively stable, but a lot of them, they're doing all sorts of different things. In the case of Miras, they bulge in and out over time, and their motion is considerable enough that you can pick it up spectroscopically. But one thing that you can also do is they have different emission lines that show up at different phases of their pulses. And so you can see in the upper right-hand corner are some traces that I took from this paper here on the left-hand side. David Boyd, who is the author of this paper, what he did was he was comparing his data that he was collecting with professional observatories to data from amateur astronomers, just showing that you can use amateur data for this particular use case. And in the lower right-hand corner is one of the graphics there. And so in the black trace, that's a professionally taken spectrum, and then in the blue is an amateur spectrum. And you can see they agree actually pretty well, with the exception of a little bit of calibration issues here and there. And so probably with a little bit more work, the resolution and the quality of the data could have been improved. But you can see there's titanium oxides or zirconium oxide lines. There's hydrogen alpha that shows up all sorts of interesting things that are in emission or absorption of this system. T Corona Borealis, again, who here has heard of T Cor Bor? Well, actually, better yet, who has not heard of T Cor Bor? Okay, we got a couple people there. T Corona Borealis is a recurrent nova. It's probably most famously known for being the star that Leslie Peltier observed for like 25 years, and then he was sleeping on the night that it erupted. It erupts like once every 79 to 80 years, and we're predicting that it's supposed to erupt soon, maybe within the next year or two. But T Cor Bor is actually a binary star system, as are all recurrent nova, and all nova are actually of that type. And as the stars are orbiting around in their orbit, they're actually elliptical. So it's not a circular orbit. It's actually stretched out a little bit. And depending on what phase of the orbit you're at, you can actually see different emission lines become present. And so on the top trace, all of the prominent lines that you see sticking up, so there's a lot of molecular lines, which that's the thing that's causing the kind of zigzaggy sawtooth pattern that you see in the spectrum. But the line that's sticking up off to the right-hand side of the top trace, that's our good friend hydrogen alpha. If you look at the bottom line there, just for reference, like the two horizontal lines that are put in the trace, those are the same amount, that's the same amount of light that's coming out of the system. So between just a few months later, the system has not only brightened considerably, so there's a lot more energy being released in the system because of a different orbital phase, and we still see the zigzaggy pattern, we still see the hydrogen lines, so you can see H alpha, H beta in the lower trace going off to the left, those are all the ones that are pointing up. And then where I have the two arrows that are pointing down, those are actually helium emission lines that we don't see at any other orbital phase. And so there was actually extra accretion that was happening at this point where there was material being dumped onto the white dwarf, and it was releasing, it was actually able to ionize helium. We also have some a BE star here, and the cool thing with BE stars is that they are decretion systems. So you think about most stars, if you hear about stars gaining mass, that's an accretion process, that's material flowing onto the star. These BE stars are rotating rapidly enough that material actually goes off the surface of the star and moves away, and it tends to be a fairly clumpy process where it's not a smooth and continuous thing. Instead, like things kind of fly off at different times, kind of like coronal mass ejections, right? We see them bulge up and then they poof away. Well, the same thing happens with BE stars. And the neat thing is that they actually show clumps of material going around the star as it slowly dissipates and it moves away, and you can pick that up with amateur-grade equipment. And then Nova SCO here. So another eruptive variable here, and the area that I've highlighted in yellow here in the middle, that's when some spectra were obtained by some amateur astronomers. On the right-hand side, we can see the Doppler velocities. This is how fast different material is moving. And you can see that at different times, the material, by looking horizontally on, say, the right trace, you can see stuff that's going out like 2,500 kilometers per second. So you can actually see material being ejected away from a star at really high velocities, which I think is really awesome that you can pick that up from the ground just with stuff that we have in our backyard. So the next question is, how can you contribute? And I'll start off by saying that science is never an easy process, but it takes a lot of training, it takes a lot of time, but we're here to help. If you get started in spectroscopy, just know that there really is a steep learning curve. This is not something that you can just go out and start getting spectra, well, with the exception of maybe the star analyzers. You probably won't be able to just go out and get spectra that's really good the first night. You're going to have to spend some time learning and trying and experimenting. Know that data is always messy, and instruments, as we heard on the Hill last night, instruments don't always function perfectly. But the nice thing is that you don't need to know everything. We're here to help. And so the AVSO has a spectroscopy section, so it's people just like you that have gone through this process before, and also several professional astronomers that can answer the higher level questions, and we're more than willing to help you out. So if you'd like to know a little bit more about this, I would say go check out the AVSO's observing manuals. So in addition to having ones for just normal variable stars, we also have one that specializes in spectroscopy, and then other things like how to use your DSLR cameras for doing photometry, for example. And just highlighting again here the AVSO spectroscopy section. This group is actually one of our most active sections within the AVSO. They meet every single month. I'm usually at those meetings, as a few folks here in the audience could attest. And so not only that, there's other professional astronomers that show up from time to time to be able to answer questions. We have an active education and training program right now. Actually, our section leader, Scott Donnell, has just recently finished producing like the first 6 or 7 courses of material that answer a lot of the fundamentals and address some issues that we've had with some of our previous training material. And we also have recommended observing programs. So you know how like most astronomy clubs, they have like an imaging target of the month or something like that. We have a grid of kind of like a 2x2 grid of different objects that you could observe that are a just let's go out and check this thing out because it's kind of fun thing, all the way up to a science thing for low, medium, and high resolution spectrometers. Additionally, we had a nice workshop that the AVSO put together in 2020 that was a several-day-long event that was focused specifically on spectroscopy. All those videos are now available on our YouTube channel, so if you want to get started there, there's another resource for self-learning. In addition to that, I'd just like to mention that the AVSO does also have a monthly webinar session. It's not always about spectroscopy. It's usually about different scientific topics. But if any of this sounds interesting to you, please check it out. These always end up on our YouTube channel as well. Lastly, where do you put your data? So there's 4 different databases that are out there that I think are worth discussing. And they cover kind of the full gamut of data that an amateur astronomer might collect. So the AVSO's database, the V in our name is for variable, and that's mostly what it's focused on, is on variable stars. And so we'll take any kind of photometric or spectroscopic data on a known variable star. But if it's not variable, we're not particularly interested in it. You can submit it at apps.avso.org/avspect. And the cool thing is that our database is the only one that's actually actively curated. So if you submit data to our database, someone will actually look at your data. It's actually either me or my staff astronomer, Bert Pablo. So like you're getting your spectra evaluated by a professional astronomer. And if we spot something that we think is wrong or something that we think is, a little bit off, we'll send you an email and say, hey, maybe could you go take a look at this? And then you're welcome to write us back. And the cool thing here is that like we improve together, right? So we're very willing to help you out there. The BAA spectroscopic database contrasts to the AVSO. They take data on just about anything. So they even have spectra on planets. And so you can see that over at the British Astronomical Society. Unfortunately, they don't actively moderate their data there. ERAS, they focus basically on things that go boom. So symbiotic stars, novae, and dwarf nova. So if you really want to focus on those objects, that's a great group, and they have folks that specialize in interpreting those types of spectra. And then lastly, BE stars, Herbig AE stars, and BE supergiants. These are all stars that show these decretion disk phenomena, or they have disks around them. This BEST database is where you would submit data for those things. And just in case, if you hear you don't own a telescope or you don't want to try to invest in, you'd like to kind of like try before you buy kind of thing, the AVSO's robotic telescope, AVSONet, does have a couple of low-resolution spectrometers. These are the Star Analyzer 100-200s. So they're available for use for any member of the AVSO. So for $95, you get access to $10,000 worth of equipment. The only catch here is that you have to write a proposal. And last year we had a high schooler that said, I think this is a really interesting object. Her proposal was a title, and then followed down below, I think this is a really interesting object. I'd like to study it for my high school project, period. And we gave her time. And so don't think this is a really complicated process, right? It will be looked at by somebody and evaluated to see if there is scientific merit, but usually you end up getting data. We are looking at adding some additional telescopes to AVSONet over the next year or two that will have these higher resolution spectrometers. And I've also been trying to work with the US Air Force Academy to get access to their 1-meter telescope with a shell spectrometer equipped on there. And in that case, the cadets at the Academy would actually be the ones collecting the data, but you would be able to get the data and reduce it and submit it to the database. So if any of this stuff sounds interesting to you, I would say, go ahead and take a picture of the QR code here. We're more than willing to help. And there's a picture of our spectroscopy group and a quick QR code, just to avso.org if your internet's not working out here. So that's it. Thank you. So that was an excellent talk, Brian. Thank you very much for coming and speaking today. So, sir, go ahead.
Back to calibration.
I would suggest if you go out and observe like an A05 and you compare it with a reference A05, you can usually correct for that effect that impacts the blue end of the spectrum. There are some cases where you can't correct it, and or there are some features of spectra that we don't want you to correct. So like interstellar reddening, for example, we want you to leave that in because reddening is a really complicated topic to begin with because you look at different areas of the sky, there's different amounts of material, and people are constantly debating in the professional literature, you know, I'm looking at this latitude and longitude of the galaxy, what is its real reddening value? So we would ask for certain things to be left in. And so if this bluing effect can't be removed from taking and looking at an A05 spectrum, I'd say probably just leave it in and submit it. Because I bet a professional astronomer could probably take it out, or depending on the science that they're looking at, it may not actually be a problem. So, any other questions?
So if you back up one slide.
Sure.
There's a telescope right almost where we live. Where is that? Right there.
Okay, which one?
The one that's right on.
On the what?
Right where we live.
Oh, up here. Oh, that's in New Hampshire. That's at Arnie Hendon's house. Yeah. So the AVSO net, you know, like most robotic telescope networks, you know, they're really costly to operate. And if any of you have remote observatories, you know, you're probably paying $500 to $1,000 per month. We as an organization couldn't afford that, and to be able to scale it out to this many telescopes is what we have. And so we adopted a different operational model where these telescopes are often in people's backyards, and they're occupying a pier in somebody else's observatory, you know, like an AVSO member's observatory. And so those folks have adopted a telescope effectively, and they're taking care of it in their backyard, and then allowing AVSO members to be able to use that telescope for doing science. Yep. So Mitchell. From which type of a spectrograph? Oh, from home-built spectrographs. Yeah, actually, there are a couple of DIY spectrographs that are back here, up at the top. So the low spec is a fairly common model. The Solex and the StarX. So if you've seen like those really cool spectroheliograph images that have been on YouTube and Facebook lately, there's with a slight modification, you can turn a Solex or one of these ML Astro devices, you can turn it into a device that you can use on stars instead, and you can get pretty good spectral resolution. And then more recently, the device on the right-hand side, this is a completely amateur constructed, from the ground up spectrometer that delivers a resolution of about 1,500, but you get the whole spectrum. And so there's lots of people that DIY them. I also had another member that he built his own spectrograph probably like 20 years ago, and he's been collecting data with it, and he submits his data, you know, in this way as well. So, you know, if you like building equipment, which who doesn't here at Stellafane, right? There's a fun project is to go out and build a spectrograph, but there's also a lot of gotchas. You have to be really concerned about stray light, and the optics don't necessarily behave in the fashion that you might expect them to if you're just used to lenses and various optical elements. So, Mark. Oh yeah, the UVX4. Yeah, sorry. Yep.
I'm in the process of building that one. I think that's a really good one.
Yeah. Thanks for pointing that out, Mark. Yeah. So Mark pointed out that I missed the UVX4, which is designed by Christian Boll, another amateur astronomer. I'd put him at the upper echelon of the amateur astronomer. He does incredibly good work.
He's the same guy that designed the Solex and the StarX.
Yep. Same guy. Yep. What is it on for that? Yeah, I don't remember what it is either. Yeah. So, okay. Any other questions? Okay. If not, I think just to ensure that we stay on time here, why don't we take a quick little 15-minute break, and we'll let Roxanne go ahead and get set up.